So we'll get started from the first question. Prove from first principles that the derivative of 2x cubed is 6x squared. So obviously with differentiation, we already know that that's going to be the case. But with first principle, how that works is we have f of x plus h minus f of x over h. And then this is the limit as h approaches 0. And then from there, we just have to substitute what that is. So f of x plus h is just going to be, if f of x equals 2x cubed, f of x plus h is going to equal 2x plus h on the inside cubed. Well, expanding this is just going to leave us with 2 lots of x cubed plus 3x h squared plus 3x squared h plus h cubed. Multiplying that by 2 gives us 2x cubed plus 6x h squared plus 6x squared h plus 2h cubed. And then from there, we just put this back into here. So this is 2x cubed plus 6x squared plus 6h squared x plus 2h cubed. And then we have minus 2x cubed over h. And that's for the limits as h approaches 0. So what does that equal? Well, the 2x cubed cancel out, so we get left with 6x squared h plus 6h squared x plus 2h cubed over h. But then from there, because this and this cancel out, we just divide by h. So we have 6x squared plus 6hx plus 2h squared. Okay, and then within the limit, if we look at it as h approaches 0, we can kind of just treat that as 0. So all the h values actually just cancel out. So all the h values have cancelled out now, and we just get left with 6x squared, which is what the differential was earlier. So next question. So we have to differentiate with respect to x. So x squared equals 2x. So in this scenario, because they multiply together, we have to use the product rule. So the product rule is just y dash equals u v dash plus v u dash. And the order doesn't matter because it's the product rule. So then from there we have, what's u in this scenario? Well, u is x squared, u dash, and what's v in this scenario? V is cos 2x. What's u dash going to be here? It's going to be 2x. And what's v dash going to be here? Well, it's chain rule, where you have to put the 2 on the outside, and this becomes negative sine x. 2x, sorry, rather. And then from there, we just put it back into the equation. So y dash therefore just equals this times that and this times that. So that's x. Let me just make this one positive. So 2x cos 2x minus 2x squared sine 2x. And that's literally it. That's how easy it is. This one here, it's not the same thing actually. This is just the chain rule. Okay, so initially we have 3 sine 2x plus 1. Well, in this scenario, there's nothing being multiplied together. It's just a 2x plus 1 on the inside is a fraction, is a function inside of a function. So it's a composite function. So we have to use a chain rule. So we put the differential of this on the outside, which is 2. And that just leaves us with 6 multiplied by, or 3 times 2 rather. And then the differential of sine 2x is just cos 2x plus 1. And that's it. That's literally, it's a one-step process. Cool. Next question. Okay, so we need to differentiate y equals 3 sine x minus 4 cos x. This is generally so easy. I do like writing out, but here in this scenario, we just don't even need to. So it's going to be 3 cos x plus 4 sine x. And that's literally it. Okay, so the function f is defined by f of x is the modulus of 2x minus 5, where x is a real number. We need to sketch the graph with the equation y equals f of x, showing the coordinates of the points where the graph cuts or meets the axis. So initially we'd start off with the graph. Well, technically speaking, we'd look at the equation, which is y equals 2x minus 5, and we can tell this is a straight line graph. So this equals y equals mx plus c is the general equation of the line, and the main thing that we'd have to look at is the two important parts, which is m, which is the gradient, and c, which is the y-intercept. So this line would look something like this. So it'd be minus 5 down here, and then it'd go up looking something like that. And we'd need to find what this point is. So the same way when this is when x equals 0, this line is when y equals 0. The x-intercept is when y equals 0. So put that into the equation. So 0 equals 2x minus 5. So x equals 5 over 2. So this point is 5 over 2. But we're asked to find the modulus of that graph. So the modulus is actually super simple. The right-hand side is going to stay the same. It's when the y values are always going to be positive. So it actually just bounces up like this. And the y-intercept is actually the y-intercept down here, but positive. And that's literally it. So it kind of looks like a bouncing ball, kind of. like a trajectory of a bouncing ball. So we need to solve this. So this one, it's really important to understand how modulus questions work, where we have f of x equals the modulus of 2x minus 5, and this, oops, I shouldn't write like that, and this, we have I guess this equals 15 plus x. So in this scenario, as you can see, 15 plus x would probably be somewhere up here, and the best way to understand it is by drawing it. So it probably looks something like this, and they'd actually be, as you can see, there'd be 2 points where they meet, this and this. And those 2 points are actually super simple to understand how or when, mathematically or algebraically, by solving it twice. So the initial first way of solving it is 2x minus 5 equals 15x plus x. And the second way would be actually the negative version, which is minus 2x plus 5 equals 15 plus x. And this is because if you look at this line here, this is when the negative version of this is, and this is the positive version. So yeah, so we solve this now. So this is x equals 20, so that's the first line, and then this is 3x equals minus 10, so x equals minus 10 over 3. Cool. So the function g is defined by this. We need to, given that it's a real number between 0 and 5, we need to find fg of 2. Well, what's f again? So f of x is the modulus of 2x minus 5. So we need to find fg of 2. Well, what's g of 2 going to be? Well, g of 2 is just 4 minus 8 plus 1, which equals 5 minus 3. So it's minus 3, so we need to find f of minus 3, which equals modulus of minus 6 minus 5, which equals 11. Find the range of g. So the range of g, you have to be really careful because you actually need to sketch this out, and it will make sense what I mean by this when I sketch it out. So we have x squared minus 4x plus 1, and we need to find the turning point of this graph. So I know it's gonna be a graph that looks something like this, but we need to find the turning point of that graph, and that turning point would actually be the minimum point. So how do you find the turning point? We just complete the square, x minus 2 squared minus 4 plus 1, and then the turning point is going to be the number 2 and minus 3. The coordinates rather, 2 minus 3. So this point is going to be 2 and minus 3. And I know for a fact that it has the y-intercept at 1 when y equals 1. So it probably looks, so if it was on the graph here, it probably looks something like this. 2 minus 3 like that. Oh my goodness. Something like that. Cool. And then from there, we actually don't need to find the roots because there's no point to find the roots. We just need to find the range of g, and the range of g which just means the values of y. So 0 and 5. So when y equals 0, when x equals 0, sorry, this equals 1, y equals 1. So that's not very necessary. When we need to find when x equals 5. When x equals 5, well, this would be y equals 25 minus 20 plus 1, which equals 6. So yeah, so the range would be minus 3 is less than or, yeah, so less than or equal to, because of the range is less than or equal to y, which is less than or equal to 6. Cool, nice. Okay, next question. So the diagram above shows a sketch of the curve with the equation y equals f of x. The curve has a turning point at a 3 minus 4 and also passes through the point 0, 5. We need to write the coordinates of the point which a is transformed on the curve with the equation y equals the modulus of f of x. Well, this is super simple. All that happens is the negatives turn positive, so it kind of like bounces up like that, and that's pretty much all this is. And then the turning point here is going to be actually 3 and 4. We need to find y equals 2 lots of f of x, f of half x. So basically the turning point actually gets twice as big. Sorry, the y, so initially, so I'll do this in a different color. So yeah, so basically what happens here when y equals 2 and then f of half x is there's going to be a vertical stretch and a horizontal stretch. So whatever happens on the inside, you kind of think about it the opposite way around. So it actually stretches twice across the x-axis, so it gets the x values get twice as big, and then the y value also gets twice as big as well. So yeah, so basically I did something wrong, so I'm just going to record it and go back again. So we have y equals 2 and then f of half x. So essentially there's a vertical stretch 2 and there's also a horizontal stretch half. And basically, if you think about it, on the inside, whenever anything's on the inside, you can kind of think about the opposite happening to it. So for example, if you have like f of x minus 1, although it's minusing 1, we're shifting to the right. So this is a translation to the right. So same with this, it's a stretch horizontally by scale factor of a half. So everything here gets twice as big. So the y-intercept also gets twice as big. So it'd go all the way up here and then go down here, and then the stretch would look something like this. So this would be 10, and this would be 6 and minus 8 as the turning point. And that's pretty much it for this question. Cool. So now we need to sketch the curve with the equation y equals f of modulus x. So it's only the x values that stay the same. The modulus of x means that it actually just flips around and it reflects on the y-axis like this. And that's literally it. So this would be minus 3 and minus 4. And then this, where it was 1 here, it'd be minus 1. And this would be minus 5 here. Cool. On your sketch, show the coordinates of all the turning points and the coordinates at which the curve cuts the x-axis. So then the curve of y equals f of x is translation of the curve with the equation y equals x squared. Find f of x. We know what this is. We know what the translation is going to be, because y equals x squared is going to look something like this. So it's going to be translation 3 to the right and 4 down. So in other words, the function would be f of x, and then there's a translation of minus 3 to the right, x minus 3 to the right, and then minus 4 down as well. So that's probably what the translation, that is what the translation would look like. And we can check how this works by doing this question here. So we have if f of x equals x squared, then f of x minus 3 minus 4 is going to equal x squared minus 3 squared, sorry, not x squared, so x minus 3 squared minus 4, which would be x squared minus 6x plus 9 minus 4, which equals x squared minus 6x plus 5. And just to check it out, this equation here is what we got, and this equation is what we had from here as well. So yeah, so this matches up and everything's correct. Lovely. Okay, next question. So we have the figure above shows a sketch of the part of the curve with equation y equals f of x equal, where x is a real number. The curve meets the coordinate axis of the point at the point 0, 1 minus k, and 1 b half ln k equals 0, where k is a constant and k is greater than 1, as shown in the diagram above. On the separate diagram, sketch the curve with the equation y equals the modulus of f of x. So the modulus of f of x is just going to be the same thing here. I'm just going to do it in the same diagram just because I can. So it will look something like this. It just bounces up and all the values and the magnitude stays the same, but the y values just become positive. And then the y of f inverse of x. So remember, I'll just do this on the same line as well. When it's the inverse, it just means if you have y equals x here, it just gets reflected on the y equals x line. So it looks something like this instead. Oh my goodness. So it looks something like this instead, like that. Cool, nice.